Hello everyone. We're waiting for more students to join. Hello once again, can you hear me?
Yes.
Okay, great. Welcome into our final lecture on distributed ledger technologies. As we mentioned, next Monday at 10:40 we'll have an exam, which will be a combination of, as in our midterm test, midterm exam, a combination of multiple choice questions, some open questions, and well, maybe some of them would be more in depth than the others, but this is a kind of format we're going to do. So basically, again, you receive the questions. You have 1 hour and a half, maybe a little bit more to complete them. So nothing that much dramatic. And in the next term, there will be a hands-on smart contracts programming module, and then it will be project-based. So we are going to implement real smart contract solutions in Ethereum and maybe even in Hyperledger at that time. Today, in our final lecture, we proceed to discuss in more detail the architecture of Hyperledger Fabric, and in particular the differences between Hyperledger and other blockchain technologies we have known so far. We mentioned some of them already, and the principal difference, if you remember, was that first of all early generation, first generation Bitcoin, second generation Ethereum blockchains They are primarily intended to support cryptocurrencies, although more and more general purpose functionality, the ability to execute general smart contracts, was developed for such blockchain. So very, very, very rudimentary for Bitcoin. A Turing complete language for smart contracts and execution on a virtual machine in Ethereum. Nevertheless, the key features are, first of all, it is primarily for financial transactions, and secondly, it is a completely public, these are completely public blockchains intended to run in a completely open, unpermissioned environment, and therefore proof of work or maybe proof of something else would be required in order to secure this network. Whereas Hyperledger was originally developed with a different objective in mind for deployment of enterprise applications. We know already that enterprise blockchain applications are just conceptually, at least, replicated databases with active replication of all nodes. We'll see now in our discussion of Hyperledger that it is not exactly correct. So in fact, Hyperledger architecture is a little bit more sophisticated than just symmetric, fully symmetric active replication. But conceptually, yes. So it is just a distributed database, and we make it distributed precisely for a number of business reasons. Some of them are related to safety, security of data. Others are related to reliability of the whole system, and so on. So we discussed these requirements last time. So now, in order to understand once again more precisely the objectives behind Hyperledger Fabric design, let us recall in a little bit more detail the sequence of state updates, smart contracts execution, and so on in, for example, Ethereum. This sequence, you can see the whiteboard, right? In Ethereum, there are some features which we took for granted, but they do not necessarily need to be taken for granted. So, first of all, not just that we have, if you remember, a fixed consensus model. Fixed, it means that it is really built in deeply in the implementation of the Ethereum node and network. It is just one fixed consensus protocol which is to be used. So there is no flexibility. You can't replace for a particular application, for example, this consensus protocol by something else. It is fixed. And also, there is an interesting implicit feature which we do not even think about. But when we start thinking about it, it appears to be just one of the assumptions. And in fact, it could be possible to alter this assumption and to do the things differently. That actually consensus in Ethereum is the same as trust model. What does it mean? Which transactions, after all, are trusted? Precisely those which got through the consensus protocol, all right? And those which are rejected due to consensus protocol, they are therefore not trusted and they do not affect the state. Whereas in fact, first of all, the consensus protocol doesn't need to be unique. And secondly, consensus and trust model could in fact be different. It's like just making a step aside. You're all familiar with C++ programming, right? Everyone, I believe, or not? You have been developing software in C++.
Actually, no, not all of us.
Not all of you, but did you have any programming language course in C++, or did you study it?
No.
No. Well, okay, then in that case, I wouldn't be able to give you that example. Actually, it is an example of how an object model in C++, the notion of the class, which is very familiar to everyone who had been doing in C++, in fact, after very close examination, appears to be not a single notion, but three notions. In C++, they are just merged together in the notion of the class, but they do not need to be. And there are other object-oriented programming languages in which all these three concepts are taken actually separately. And when we start looking at this paradigm from that angle, it appears to be very, very instructive actually for understanding both C++ and other languages. Same thing here. When we started, and C++ was the first general purpose object-oriented programming language, so when this notion of the C++ class, which is the unit of encapsulation, inheritance, and polymorphism was introduced, then it was like just an indivisible notion that encapsulation, inheritance, and polymorphism come into a single programming language construct, but they don't need to be. In a similar way, in the model of our blockchain, consensus and trust do not really need to be equivalent. And in Hyperledger, I will show that they're indeed not the same. So for the moment, let's see what are the features of Ethereum. Also, can you please recall at which point exactly execution of smart contracts occurs in C++, in Ethereum transactions? So you see, first clients propose new transactions. Transactions are inserted into the network. There is a queue of transactions. They are disseminated across the whole Ethereum network. Okay. The mining nodes start to build blocks out of these transactions. At this point, the smart contracts are already executed or not? A transaction is coming in into a particular node, then disseminated broadcast. And you remember in Ethereum that a transaction may contain both actually value, Ethereum value, and data. Data precisely serving as the argument for smart contract invocation. And it is possible that the destination of this transaction is an address associated with a smart contract. So now it is broadcast to all other nodes. Okay, nodes are building a candidate block. Each node builds a candidate block from the queue of transactions. Okay, transaction is again value and data. So smart contract execution, does it happen prior to including transaction into the candidate block or afterwards? At this point, if the transaction destination is a smart contract, did it run already or not yet? What do you think? From what we know about Ethereum. No idea? The answer is, of course not. And by the way, please pay attention to this. This may very well be one of the exam questions. At this point, transactions are exactly pairs of value and or data. Both value and data can potentially be empty. Transactions are not executed at this point. They are queued, prioritized based on the transaction fee, which the miner would earn. In this case, the transaction fee is given in terms of the gas price, and candidate blocks are built. Now, by using the consensus protocol across all nodes, and this consensus includes proof of work. So once a candidate block is built, each node is trying to hash it. You remember, trying to hash it, then one of them succeeds. A successful candidate block is again disseminated to all others, but it might be that two blocks succeeded at the same time, so a fork occurs. Anyway, now a consensus protocol is executed, and only then, when we know that each particular node knows that this is the block it is going to add, it may very well be that the blockchain forks at that stage. Never mind, it will reconverge later on. But at this point, state update occurs. So when a new block is finally inserted into the blockchain, then at each node, according to its own view of the consensus, it may, as I say, result in a fork, but it will converge later. Then new block is committed, and at this point, smart contracts are run. And this happens by all nodes, and in particular, if they are on, they update the state associated with the corresponding address. It could be, you remember, there is a storage associated with the addresses which are smart contracts, and that state is addressed. Obviously, what is again one assumption? An interesting thing is that, okay, we have consensus first. We have consensus first, and then we run smart contracts. What do you think is an implicit assumption? Okay, storage updated. Smart contract storage updated. Because, and here as well, at each node, because we run the consensus first and update the storage second. Yes, it might be that there would be forks, but apart from forks, we have an implicit assumption here that, you know what, the storage is to be updated deterministically. And this is a very important assumption. So a smart contract in Ethereum must run deterministically. What do you think what do you think it means actually? Smart contract is deterministic. It deterministic.
If we will run it a few times, it will be always the same?
Yes, running a few times on the same input, and the input is the data in our transaction, it would produce exactly the same state update, which is then memorized in the storage. Exactly. Which means that what, for example, a smart contract cannot do in that case. Just a very, very, very simple programming construct, which is not allowed for a smart contract in that case. How can you make your program do? Yeah?
Mutability?
You say what? Mutability?
Yeah.
How can you write a program in your favorite programming language? How could you, there is an input and output. How could you make your program non-deterministic? So given the same input, it would nevertheless produce multiple outputs on different
Using some probabilistic data structures or something like this?
Probabilistic data structures. So what are the typical probabilistic data structures? How can we make a probabilistic data structure? What is the basic building block to make a probabilistic data structure?
Call random function, like randomization function.
Yes. So basically, the easiest way, of course, there are some other ways. So for example, a very easy way to make your program non-deterministic is to access some undefined memory address. But in smart contracts, it wouldn't help you making your smart contract non-deterministic because all memory is initialized to zero, zeroed out. So actually achieving non-determinism in your smart contract execution is not a very easy task in a well-designed runtime system. But in general, how we achieve it, really by introducing some kind of a random, let's say, number generator or a random values generator. So non-determinism typically via some random values generation. From your, well, any mathematics or cryptography or whatever, cryptography probably, course, do you remember how random values are generated? If we want to make our smart contract non-deterministic.
We should use some kind of counter, which is like maybe time, maybe something else, maybe even the hardware, some device, if it's like usual PC.
You are right. You are right. So basically, if we look precisely at how this non-determinism can be achieved, it is via extra inputs. So you really need inputs. You really need to get access to some external data to the environment. So for example, yes, you can initialize your random number generator using a timer, or it could be specialist hardware, or it could be some entropy generating software which read the state of your overall memory, hard drive, mouse movements, whatever, entropy gathering. source, and so on. If you don't have access to any of them, then you wouldn't be able to achieve true randomness. The only thing you can do is to build, in that case, a sequence of pseudo-random values, which start with the same value in the state, for example, 0, and then actually it deterministically computes new values, but the sequence of these values, if examined for statistical properties, may look like a sequence of random numbers. So statistically they appear to be random, whereas in fact we do know that they are not at all random. There is an algorithm, and in fact deterministic algorithm, producing subsequent values. So it would be statistically random, but in fact pseudo-random, and in fact deterministic, still a deterministic sequence. True non-determinism is only possible if you have other inputs like timer, specialist hardware, etc., etc. And obviously the Ethereum virtual machine, your code is the bytecode of the virtual machine. You are not able to execute arbitrary code on Ethereum. The Ethereum virtual machine does not provide you with that. So Ethereum virtual machine does not allow non-determinism. And this allows us really to construct a sequence of transactions first, and only when we really committed our block into the blockchain, then perform the actual execution of smart contracts. So altogether, the whole model of Ethereum is called order. By order, it means first introduce a new transaction into the blockchain and then perform consistent. So all this part is called the ordering stage, order. From introduction of a new invocation of a new transaction up to and including the consensus protocol. And only after a commit has happened, it is the execution of smart contract. So it is order, execute, order exec type of blockchain architecture, which is only possible for deterministic smart contracts. So that's one limitation. This model doesn't allow you non-deterministic behavior in your smart contracts. Obviously, you may say that you don't even want non-deterministic behavior because, yes, after all, it looks like it contradicts the whole notion of consensus. Yes, it would contradict the notion of consensus, but only if you do execution of smart contracts after ordering. In that case, of course, non-determinism is not allowed in smart contracts, obviously. If, however, you execute smart contracts first, and then you perform consensus not on inputs, but let's say outputs of your smart contract execution, then it would at least theoretically become possible. Whether it is a good idea or not, it is a different question, but theoretically it would become possible. And another problem, what do you think is another problem in Ethereum in that case? I wouldn't say it is a big problem, but nevertheless. You see, if we already know that by construction, our smart contracts are deterministic, and we have already established the ordering. So our consensus protocol says, yes, this block composed on those transactions 1, 2, 3, 100 is to be appended to the blockchain, committed to the blockchain. Why do we need to run this smart contract exactly on the same exactly in the same way on each and every node. This is a waste of resources. We already know that this is the sequence of transactions to be executed, all right? That all transactions are deterministic, and therefore with this block being committed, the result of running smart contracts would be same at each and every node. And nevertheless, we require each and every node to execute the same smart contract, possibly expensive, possibly running on a lot of gas, wasting actually computational resources. Well, you can say we have already wasted a lot of computational resources here. Here is a big waste, right?
Probably because we need to make sure there is no malicious node or something, and that's why we need to duplicate everything, because one node can be out of the network in the next second or something like this. So that's why we need to run it on a few machines.
You are right. You are right. So there was already a big waste of computational resources here in proof of work. There is a second waste here in smart contract execution. But when we start thinking about it, it appears that we can't do it otherwise. So really, if we do not execute our smart contract on each and every node, then yes, it may get to a malicious node which executed wrongly, and there is absolutely no way to trust some node with execution of smart contracts so that the value of execution could be then accepted by all other nodes. Unfortunately not. So basically a malicious node with this model, a malicious node would only make it wrong for itself, because this happens after the consensus. Okay, a malicious node wrongly executes a smart contract, so it corrupts only its own state, right? Because the consensus has already run. If it executes the smart contract wrongly, it only corrupts its own state. Other legitimate nodes still perfectly correctly execute our smart contracts. So that's okay. But that's because the environment is completely untrusted and non-permissioned, unpermissioned. If we move into permissioned enterprise environment, so at least we know the identities of the actors, and there is some kind of, if you remember, even administration observing the performance of the whole network. So the network is primarily for reliability, fault tolerance, rather than for conquering deliberately malicious nodes in an enterprise environment. Then the situation changes, and it appears that maybe we can do it in such a way that we don't need to execute our smart contracts on each and every node. So in that case, in an enterprise network, we would eliminate actually both sources of waste. So you see, the first waste is through the proof of work. We may avoid it in an enterprise system because all nodes are statically configured and permissioned. And the second one, we can either completely eliminate or maybe at least reduce the second waste, the second stage of waste, by executing our smart contracts in a permissioned network on some subset, at least, of nodes rather than everywhere.
And in this case, we will lose the trustless property, right?
We will reduce our property, not lose it completely. It depends on how we do it. But yes, in enterprise environment, as I say, how trust is built in Ethereum. In Ethereum, the trust is simply built by numbers. So it is a completely democratic system. What is considered to be correct? Where is the truth? The truth is what the majority has voted for. all right? If the majority of the people votes for the flat Earth, you know that the Earth is flat rather than spherical in Ethereum, then we'll have to accept this because our trust model says exactly that. So it is a majority vote, right? Which means that, you know, this kind of democracy is not probably optimal in all situations. In an enterprise network, the trust is, as you see here, consensus is a trust model in Ethereum. In Hyperledger or possibly other enterprise models, consensus is not the same as trust model. That trust first is established. Well, trust is a much more complex thing than consensus. In Hyperledger, I have already mentioned that, but we'll repeat this point today. Trust is probably three-staged. The first stage of trust, I can put it here in the corner, then we'll see it. In Hyperledger, let's say Hyperledger Fabric. Trust is first of all via initial permissions, certificates. So an arbitrary entity is not allowed to enter the network. Only permissioned nodes or permissioned users which present the corresponding cryptographic certificates. Consensus is not really a way of achieving trust, although it may be as well. But it is only, I would say, a secondary use of consensus as a means of trust in this case. Primarily, consensus is for not for trust by itself, but it is for consolidating real-time state. So the consensus protocol is primarily, first of all, to merge back the forks. Why do the forks occur? Primarily because we can do transactions at the same time which are received by separate nodes. So the first node receives one transaction, the second node receives another transaction. So there is an inherent real-time distributed non-determinism. So the consensus protocol is primarily to conquer the issue of real-time non-determinism. And yes, possibly some faults in the nodes, but not deliberately malicious nodes which could be introduced into an enterprise network with any numbers. That is prevented by the first one, so by means of certificates. And also, so I'm not even sure whether consensus should be mentioned as number one means of trust, but let's say yes, but definitely not the first one. And there are also other means of trust in Hyperledger, which is precisely the mechanism for transaction validation, so so-called validation nodes and transaction validation, which we'll see shortly. So consensus is not a primary means of achieving trust in HLF. So trust is much more complex thing in that case. By the way, I'm describing this in, I would say, layman words. Ideally, what we would like to do is to provide a formal model which would formalize the notion of trust and consensus in Hyperledger and prove that certain properties hold in that case. To the best of my knowledge, the overall protocol of Hyperledger Fabric has not been formally verified yet. Our inner chain protocol yes, it has been formally verified, although it is a more simple one than Hyperledger. We are less flexible in the chain, as I mentioned. The blockchain system, the distributed ledger system currently under development in Napolis, it is definitely less flexible than Hyperledger, but the advantage of having this less flexible architecture is our ability to formally verify it. And in this case, actually, we are following more traditional order and then execute sequence, like in Ethereum, plus certificates, plus only deterministic sources of information. And this allows us to formally verify that, for example, consensus really results in state convergence across all nodes. So, okay, what can we do for Hyperledger if we want to depart from this Ethereum model? Sorry, one more point. One more point in that because the transactions are executed by all nodes here, then obviously all transactions, it is a fully open, public, etc., etc., etc. network. All transactions, inputs, outputs, code, and so on is visible for everyone, which means that the Ethereum network does not possess a certain very important quality, which we deliberately sacrifice because it is non-implementable in a fully public environment. How is it called? Confidentiality. So it is a total lack of confidentiality. Okay, total lack of confidentiality. That is deliberate. So in general, it is, maybe it is a good thing. All your Ethereum or Bitcoin transactions are actually traceable. Well, they are traceable at least to the extent that you know, and everyone would know by applying sufficiently powerful search algorithms on the blockchain, what are the inputs or outputs of a particular transaction. So, for example, if you are trying to do something illegal, this is very difficult to do in Bitcoin or Ethereum. In fact, quite difficult to do. I mean, no, it is not difficult, but it is difficult to do safely. Suppose that you want to buy a machine gun, paying for it in Bitcoins. And there is indeed, just, an arms dealer who is ready to sell you a machine gun. Then he is caught. And all his transactions, he is caught. He is associated with his public key by law enforcement agencies. And it is known, all transactions in Bitcoins destined to this public key, they were probably for weapons purchase purpose. Can you hide in the blockchain network? Because there was also your transaction. You send Bitcoins to that person paying for the machine gun. Okay? What will happen to you then? What do you think?
Actually, it's not like there is no way to prove that you send this not by accident, that you're actually holding this account or not. It happens even with the usual accounts. It's hard to prove that it's let's say you were using fake documents. Legally it's hard, but technically, of course, it's connected.
I can
but
tell you
there's no way to connect.
I can tell you. So yes, to prove that this transaction is deliberate is quite difficult. but it is already sufficient to at least arise some suspicions, some some uh, warranted suspicions against you. Obviously, you would not, in this case, associate your public key with your personality. So you would not get a certificate that this public key really belongs to you, right? So you would have just generated a public and private key pair and use your public key uh, in order to do what? In order to pay with your bitcoins, you need to get your bitcoins from somewhere. Okay, and then you use your private key in order to authorize a further transaction to pay for the machine gun. So what the law enforcement would see in that case? They would see, okay, this public key send the funds to the machine gun dealer. Okay, where did this public key get the bitcoins in the first place? Where would you get the bitcoins? You would get the bitcoins from Binance, in that case, from the exchange. And unfortunately for you, at this point, your anonymity is no longer possible because a regulated or semi-regulated exchange, in any case, operates the know your customer, know your client KYC policy. So you need to authorize yourself to the exchange, providing your true proof of identity before you can really buy bitcoins at the exchange. At that point, initially, the bitcoins are linked to a wallet, I mean, a public key, which is notionally not yours. It is the exchanges, all right? But then it is sent it is sent from the exchange wallet, which is from the cryptography point of view, it belongs to the exchange. But from the legal point of view, it belongs to you because it has been associated with you. Then it is sent to this, illegitimate account, and therefore your anonymity is broken, is blown, and it becomes at least clear for law enforcement that you paid to that person who is dealing in arms. And this is sufficient to just, authorize a search warrant at your place, and a machine gun is found. And, all bets are off. Bitcoin and Ethereum provide no anonymity, no confidentiality. There are some ways of how this anonymity and confidentiality can be enhanced. There are, for example, some kind of mixer exchanges which do a very illegal practice from any anti-money laundering regulation point of view. It is called layering. When your transaction is split into a number of other transactions, then they're mixed with others, and then you receive your output on a completely different set of wallets. Which would probably make it more difficult, but still not impossible, to associate the final payment with your original identity. So in that case, if, for example, a mixer is used, in that case, it would be, so for example, a mixer here, from multiple accounts in a mixer, there would be a transaction into first of all, maybe your consolidated account, or maybe just multiple accounts, or the eventual payment happens here. And obviously, because there are multiple transactions, there are multiple inputs here, and still it is possible to say that there was a many-to-many, you remember, many-to-many transaction. So in this transaction in Bitcoin, one of the outputs, or maybe yes, full output, occurred here, And one of the inputs, maybe not a direct one, was eventually somehow associated with you. It is not sufficient to prove that you did it deliberately, just, you know, for the purpose of buying machine gun, but still your real identity would sooner or later, by applying sufficient intelligence, would be discovered. A short break, please. Okay, we're back. So there is no confidentiality in Bitcoin or Ethereum, right?
Yeah, but there is the one flaw which is not that practical, but still exists. You can anonymously mine coin, like just put your, like earn basically. If you
Oh,
will
yes.
earn the
Yes,
coins.
if you are a miner, you are right. Yes. In that case, you originate this cryptocurrency. It is not practical. And I would say that you would, in that case, probably run into huge expenses related to mining, which may or may not be economically profitable. But yes, you are right. If you are a miner, of course, then the whole network can become anonymous. Fortunately, mining is difficult, because should mining be easier, then you are right, everyone would be able to execute this illegal sequence. But in general, there is no confidentiality in Bitcoin or Ethereum, apart from yes, the scheme you have mentioned. Whereas in enterprise type of setup, we may want confidentiality, and for that reason, uh, we probably want our smart contracts to be executed not by all nodes. We may want them to be executed again only by a subset of nodes, which are, for example, authorized to do so or to see the result of smart contract running, and so on. Therefore, compared to uh, compared to Ethereum or Bitcoin, we have a completely different scheme in Hyperledger Fabric, which is called first execute smart contracts, then order. Order means apply consensus, and only then it means validate. Actually, order and validate are a kind of same step, but for some reason in Hyperledger, they are logically considered to be different. I would say there is a much bigger difference between what we do in execution of smart contracts and in the second two stages. Order and validation are quite closely related to each other compared to the execution phase. Now, in a second, we'll see how it all works in Hyperledger. Okay, let us see how it is done in Hyperledger. So, execute, order, validate, and update the state. First of all, in Hyperledger, there is a separate set of nodes which perform two tasks. First, when a transaction, and in general, the transaction would contain a smart contract because there is no value transactions in Hyperledger, so any transaction is simply a transaction to a smart contract. It couldn't be otherwise. They so-called simulate transactions. What does it mean, simulate? Simulate means really execute smart contracts. Why we do not say, why this strange term simulation? Really because we still don't know what will happen actually with the result of this execution, whether it will eventually come to the point of updating the state. It may or may not be. So smart contracts are executed or simulated, as the term says, for Hyperledger on a particular subset of nodes, so on a subset of peers, not on all of them. And because this is combined with other trust mechanisms, this is considered to be okay. Moreover, for each particular smart contract, we can say it is to be simulated on this subset of nodes. This smart contract runs, for example, on 10% of nodes. Another smart contract runs on 15% of nodes, and we explicitly say on which. Then there is a separate stage here. Not only smart contracts are executed, but there is also a so-called endorsement state. Endorsement is a kind of, again, consensus, but it is different from the consensus which occurs here at the ordering stage. It means that if, for example, n nodes have executed, and this n is typically less than the total number of nodes, are executed the smart contract, then there is a simple rule, typically amount of n, which would need to, let's say, get some kind of formal endorsement of the smart contract. So basically say that exchanging the results between themselves, confirming that the results are correct. It doesn't, by the way, mean that the results need to be identical. It is quite possible that non-deterministic smart contracts are executed. Nevertheless, the results are endorsed by this amount of n, and for example, some kind of average obtained as a result of this non-deterministic execution. This is perfectly okay because execution of smart contracts and endorsement occurs first, at the very first stage, prior to attempting to modify the state of the whole system. Then there is an ordering stage. Ordering stage is really concerned with the system-wide consensus. So the nodes which executed, simulated, and endorsed smart contracts, they propagate the endorsed values, which are called read-write set, to other nodes, and these sets are ordered. By the way, we'll see in the next slide actually here that because typically each smart contract here, smart contracts are all these different colors and shades are different smart contracts. In that case, because only part of smart contracts is executed, each smart contract is executed by a part at a part of nodes, some subset of nodes, which means that multiple smart contracts can be executed at the same time by different nodes, which solves again the problem of throughput of the whole system, because we can use this large number of peers in order to parallelize execution of smart contracts, even if they are expensive from the execution point of view. There is no gas in Hyperledger. The code is supposed to be trusted because it comes from certified, authenticated sources. And you can optimally use the whole computational power available in the network by running multiple smart contracts in parallel. Therefore, from each smart contract execution upon endorsement, we receive the output, which is called this read-write set. These read-write sets are now ordered in the system, which means that consensus is achieved. In Hyperledger terminology, consensus is the term for consensus is atomic broadcast. Obviously, broadcast is not atomic. Broadcast in reality, in a distributed real-time system, cannot be atomic. Only if you use very, very specialist hardware in a local cabinet-wide network, you can do something like atomic broadcast, but in reality, it wouldn't be the case. It is atomic notionally as a result of consensus achieved. There is a peer-to-peer exchange of these read-write sets, which are queued, then a certain protocol of consensus is applied to them, which tackles two problems, as I said. First of all, a real-time non-determinism of values being generated and values being sent and received. So there is an inherent non-determinism from the real-time point of view here. And also, yes, it would conquer the problem of potentially faulty nodes. Faulty, but not deliberately introduced multiple Byzantine treacherous nodes. As a result, this ordering service by itself is called stateless because it acts on the set of sequence numbers of transactions and not with the state of each transaction by itself. As a result, the output is really an ordered set of transaction outputs, which is accepted by all legitimate, all valid nodes. Here, we're dealing with a system-wide propagation of value. If execution of smart contracts can only be done by a subset, here the values are propagated to conceptually all of them, at least all of them which are authorized to see the corresponding transaction output. Then there is a second stage, well, third stage actually, which is validation. After the transactions have been ordered, they are validated and across multiple nodes. Here, invalid and conflicting transactions are eliminated due to a uniform ordering. And finally, the state is updated across all peers. So here, for example, the nodes are functionally I would say, classified into ordering service. OSN is ordering service node. The nodes which execute smart contracts, and there are actually other nodes which you can see in this sequence diagram. So from a client, there is an invocation. Then chain code execution is precisely smart contract execution. Chain code is the term for smart contract. The results are being endorsed. Then they come through the ordering service. And eventually a single view is available to other peers which are not involved in either ordering or endorsement. So the final peer, any abstract peer, can see a uniform state of the world after this endorsement and ordering have been achieved. So basically we have three types of nodes here. Those which simply perform chain code execution, those which perform endorsement on the results, for example, 3 out of 5 or something like that, those which perform ordering, which may again be not the whole set actually, and all nodes in general, which as a result simply share the same state. So they could act as consumers to the same state, although functionally dedicated nodes perform chain code execution, endorsement, and ordering means running consensus among them. Again, you do not need to get absolutely all nodes in order to perform ordering. A subset is sufficient in order to conquer real-time non-determinism and potential Byzantine faults. Ordering service is, as I mentioned, is implemented using typically Kafka Java technology, although it is just a reference implementation and as currently available on Hyperledger, and it is possible that other implementations would emerge in the future. From my personal point of view, Kafka is a bit heavyweight, but compared to proof of work previously used in Ethereum and Bitcoin, it is probably more than adequate. A typical, let's say, financial transaction happens as explained here. So first of all, in order to transact between two parties, notionally, which are typically known as Bob and Alice, you remember, then they first need to authenticate themselves to the system. So receive the certificate and produce the certificates to the system. So they would be able to do transactions at all, which is done with the help of certification authority. This is a part of Hyperledger architecture. Then they do not, well, first of all, they propose a transaction, but so propose a trade here, but it is not a trade yet. It needs to be, as we know, it needs to be endorsed first, as we have seen. Then the proposed transaction is broadcast to all endorsing peers, not all of them. A voting is performed on those endorsing peers amount of n. A client collects all endorsements and then produces the uniform view to the ordering service, as we have seen. And the ordering service, yes, it is Kafka based. But this is a technology, implementation technology feature. Then the ordering service commits this transaction into the sequence of transactions with uniform sequence of numbers in the whole system. And this committed block is now disseminated across the whole network using this peer-to-peer so-called gossip protocol. And eventually we result in a transaction being so-called accepted by the whole network, which means that it is a uniform view of this transaction available now for the whole network to see. So that's a workflow in Hyperledger Fabric. Unlike, and this is very important also, unlike Bitcoin or Ethereum, you do not need to write your smart contracts in some domain-specific language. You can use general purpose programming languages. It may very well be Java, for example, in order to implement a smart contract, which is both actually a good and a bad thing. To be honest, I do not like this idea very much. My view is that these transactions can better be implemented in verifiable domain-specific languages for a number of reasons, both actually reliability, resource utilization, formal verification, and so on. In Hyperledger, when you run your transactions in implemented in an arbitrary programming language, how would endorsing peers be able to safely run those transactions? Imagine that it is an arbitrary programming code, either Java code or maybe even executable code. It can only be run in some isolated environment. Typically, Docker in Linux is used to that end. So a smart contract invocation is very heavy weight. A transaction needs to be received, then the whole execution environment set up to safely execute this transaction, containerized, executed, and the output received back by the endorsing node. It is a heavyweight operation. There is no gas, so this container may be subject to its own policy, for example, using whatever software to control containerized resources in Linux. You can set up the maximum number of, let's say, CPU, the maximum CPU time, memory utilization, disk IO utilization, and so on to run this smart contract. If not run successfully, then execution is simply aborted and the corresponding executing or endorsing peer fails to execute a smart contract. But the cost of this is significant complication of smart contract execution. They can be as heavy as you like, provided that they are executed within the overall framework on a particular, for example, Linux node of how containers, Docker containers, or any others can be executed. So,
what about type-safe languages and memory-safe? I mean, the ones which can be fully verified compile time.
That's the whole point. They can be verified at compile time, and it is perfectly okay. But typically, Hyperledger does not take advantage of that. Even if you know that your code is formally verified and, for example, its execution time is limited and so on, Hyperledger, due to its fairly flexible architecture, doesn't know anything about that because it is not its own code. It's not bytecode. It is not something which it can understand. Whether you can configure your endorsing peer in that case to avoid containerization and run it in, let's say, unrestricted environment, well, the answer is, of course, you can. Because after all, the whole Hyperledger is open source, so you can tweak it in any way you like. It is not the way it is supposed to work. So the way it is supposed to work is completely different. So it doesn't put any trust in the code being executed by itself, and the trust is put on the container. If you know that your code is type safe or cryptographically signed or verified for termination with very limited resource utilization and so on, you can probably, yes, modify your endorsing P in such a way that it would execute this code straight away. But that's not the generic way in Hyperledger. But it is up to you. It is open source. My personal feelings are that it is in general unnecessary because most of industrial applications, they do not need to run arbitrary code anyway. On the contrary, smart contracts in dependable, highly dependable industrial applications would typically, as in our inner chain, be type safe, validated, and possibly even formally verified pieces of code. Not because the major concern is about resource utilization or that endorsing P would crash, but simply because you need to enforce functional correctness of your code if it is a mission critical blockchain environment. If your blockchain environment controls something important like aircraft fueling or let's say distribution and reselling of electrical energy or things like that, then you need to do a lot of work in order to verify the validity of your smart contracts. And that's why, in general, that was one of the objectives why we started actually with our own in-the-chain formally verified blockchain technology, rather than implementing everything in Hyperledger. It was possible just to take Hyperledger and implement business solutions on top of it. Hyperledger is still generation 3 blockchain technology. Generation 1 is Bitcoin, generation 2 is Ethereum, generation 3 is general purpose blockchain, typically manifested by Hyperledger. Generation 4 is our formally verified in-the-chain. At Innopolis, we're developing the 4th generation blockchain, as you already know. I would probably stop here. In the next term, you will have the smart contracts programming module. And what I think we'll do, we'll take either Hyperledger or Ethereum. We'll see. Maybe Ethereum is easy because you can deploy it everywhere on everyone's computer, and implement something like distributed exchange, DEX. Distributed exchange, which allows you to, well, first of all, a certain coin, and a distributed exchange for that coin, which allows you to exchange it for Ethereum completely in the blockchain without any centralized applications which could take your funds and not give them back to you. A distributed exchange based on storage, persistent storage of smart contracts, would be perfectly safe from that point of view. So next term, you are going to have very, very, very exciting DEX implementation. Everyone is encouraged to do that. I think we are primarily done for this course, and I would be very happy in the remaining minutes to answer your questions about the course as a whole. Maybe hear some feedback or suggestions from you, and we are all set for an exam on Monday. It's your turn, please. All our videos and slides and papers will today be in Moodle.
Thank you for the course. It was really interesting. And I just wanted to take a look more at the 11th slide. There was some, like, is it typical architecture or something? You skipped it so fast, so I couldn't.
You mean slides from this lecture?
Yeah, this lecture.
I will put them in the Moodle. These infrastructure components like ordering service, membership.
Is it just a general like approach to build a ledger system?
You are interested in the general approach to build ledger systems. You know what? Apart from that, there is a very nice book which is called Build Your Own Blockchain. I will send it to our Telegram group as well. I can't put it in the Moodle because this is a sin nearly the same as selling a machine gun, but I will put it into Telegram, okay?
Yeah, thank you.
Okay. Thank you for reminding me. It's actually a very good idea.
And one more question. Yes. While I was doing this project for the like substitution of the labs, I noticed there are a few ways to, like, there's in general one way to prove that you're a holder of some account, to sign your public address and just send it to the server. It's clear, but there are no common protocol for this, right? Because all the implementation I've seen, they're quite like you need to rely on this. What, for example, what this thing with the fox on it, how it's called, MetaMask, what they do, they just inject in JavaScript object into every website, and you're able to connect to it. But it's not quite safe because you just rely on this extension, which is
yes.
basically allows every website you browse call an API, and if there will be a vulnerability, a way to execute something.
Yes, a MetaMask is a browser-based wallet. I think it is a good thing actually to maybe explore the Ethereum network, but it is definitely not a safe way to transact large amounts of Ethereum. You really need.
Yeah, I was trying to find these things like the tools, but there are no common safe. Let's say for the web, we can just use HTTPS, and it's quite safe, like, safe enough for general purpose, and it's common. You like let's say REST or RPC over HTTPS, but to communicate with the Ethereum or any other blockchain from like client side, there are no protocols which are open and
That's
used
true.
everywhere.
Because it is not part of the Ethereum protocol. Actually, the client is just an arbitrary software which on that end adheres to the Ethereum protocol, but it can manage your transactions, your keys in any way this client would like to. You're asking a very interesting question. So about a comparative, let's say, safety and security analysis of multiple clients. If there is no single one, which is a standard, then what would be the pros and cons of the existing ones? This is a very interesting point. I don't think there is any formal analysis of them. Let us do some kind of search and see how at least security and safety auditing of various Ethereum clients had been done. To that end, I would probably be feeling more towards command line clients, which are most safe. And you know what? A very important thing is to provide this air gap. You remember air gap between your keys and the network. And this air gap in any client could be provided by, for example, typing in the password or passphrase manually from the keyboard. In this case, the full set of information which is required to authenticate your transaction is never stored in any computer storage and cannot be leaked. Although, again, if you got a Trojan which reads your keyboard, I would say on Linux it is pretty much uncommon, but nevertheless, then there are problems with you. So all in all, my advice would be for high value transactions, use hardware wallets, which are only temporarily connected to your computer storage, passphrases written on paper, a Linux or a FreeBSD operating system. I haven't heard much about, let's say, any malware or worms or whatever for example, for FreeBSD. For Linux, maybe there are some.
Actually, sometimes it's quite a challenge to even run your software there.
Even a challenge to run this software. So the security path becomes so complicated that it provides more problems for you, right? Rather than for the attacker. That's what you mean. It might be, but in
sorry.
Non-standard operating systems, command line clients, passwords, passphrases written on paper to provide their gap is probably a state-of-the-art safety feature, I would say.
Yeah, it's fine for, let's say, node holder or someone like this, but what about the DApps, the like distributed applications, and they can be, let's say, housewives for using this, and if there are no common protocol between these wallets, then how the developer should.
It might be a problem. So in that case, for each distributed application, you basically reinvent the wheel, specifying your own protocol, and then you are responsible for all those safety and security features, I admit it is a problem. What does it mean, by the way? It simply means that the whole technology, especially for distributed applications rather than smart contracts, you're actually right that you highlight the difference between them. In the next term, we will consider the difference in more detail. What is the difference between distributed applications and smart contracts? That simply means that the whole technology is not mature. And as it happens with immature technology, there is a lack of standardized protocols, standardized security features, and so on. They will emerge, probably. But for the moment, you are absolutely right. You are pointing out that the technology is not mature. That's true.
Thank you.
Okay, then. Thank you very much. Thanks to everyone for attending our course. And I will see you next Monday at 10:40 for the exam. Thanks a lot.
Bye. Thank you.
Thank you. Bye.